even very obvious things about this, the things which you think, oh, that's stuff, don't bother saying that because everyone can see that. I promise you that even very obvious things will be useful and interesting to us later, okay? So, what did you see? Anyone? Anyone want to start us off? Yeah, Oscar.
It's like a cone shape.
Yeah, it's a conical shape, isn't it? Okay. Now, I know there's some, if you have a look at the glass, you know, parts of it are sort of, the outside is curvy, but if you look quite closely, if you look at the inside of the glass, if you look very closely at about here, right, you can see it actually, it's very, despite the curvature like this, it very closely matches a straight sort of cone shape with a pointy bit at the top. It goes further inside sort of the shaft, okay? So, good observation. Excellent. This will be very important to us. Other observations? Come on, tell me you saw more than the fact there was a cone.
When you pour the water,
Well,
water level rose.
Okay, alright. Water level. The water level rose. We're going to talk about that quite a bit, actually. What else? Yes?
The speed of which the water rose became slower as time goes.
Okay, so how can we, that's exactly true. Can we say it in any more succinct way? Because that was a lot of words. And I do want some words. Words are important.
T increases.
The rate of what do you call it? Of height increase? Height increase? That rate, it got slower, didn't it? The rate slowed. Okay. All right. Anything else? Sorry, say that again. It overflowed. Good. All right. Anything else? Yep.
Your pouring speed was constant.
Yeah. Okay. I tried. The pouring rate was. I just put that. And the way that I was measuring it was I was trying to watch. I know this is not very scientific, but I was trying to watch the diameter of the water that was flowing out. That's the way that I was measuring it, okay? Initially, I thought about doing it by sound, but as you might have noticed, that became an increasingly less useful measure of how quickly I was pouring, right? Okay. Was there anything else that you think was interesting? Any other things that you saw? It's a nice little set. I admit I didn't get you to come out and have a look at this thing, but if you had to estimate, how wide do you think this is, roughly? What would you guess? 20? 24? 25? I measured it. I actually did go and measure it. And I measured it at, I think the diameter was 26 centimeters. 26. So, pretty reasonable guesses. For the sake of simplicity, I'm just going to call it 24 because that's going to be useful to me later on. Okay. Now, how tall is the thing? How tall is it? Well, obviously you've got the height of the whole thing, don't you? Okay. But what height do you think might be more useful to us? Probably just the cone, which ends somewhere around here, doesn't it? Okay. Now you have a look at that versus this. Okay, versus the top and compared to the width. I don't know. What would you estimate?
24.
It's not as tall as it is wide, okay? But again, for simplicity, to help us think about this a bit later on, I am going to call it 24, okay? I'm going to call that the height. It's close enough to 24 that it's not a meaningless kind of number to put on there, but it isn't 24. It will just make things a little easier to think about later on, okay? So, what topic are we looking at today? We're sort of looking at a super topic, if you like, within which we're going to focus on a few different things, okay? The super topic is called Applications of Calculus. Oops. Of Calculus to the, does anyone know? Physical world. To the physical world. I believe I just barely heard 4 syllables in that, okay? Now there's lots of things underneath this. The reason why there are lots of things is because calculus has many applications to the physical world. Tons and tons and tons of them. In fact, calculus was born out of trying to understand the physical world, in particular, things that change, okay? Now, that makes the first subtopic underneath this super topic, related rates of change, a good place to start. Okay? Now, I do say start, and I started with this very deliberately because mostly when this is taught, and when I've taught it in the past, we don't start with this, we start with this. And mathematically, I suppose that makes sense because you have been working with calculus for some time now, right? But I wanted to get this in front of your eyes so you could think about this, and so when we start doing some of this, you'll be able to fit these kinds of things into that understanding rather than the other way round, okay? Because I think this is all intuitive to us. This makes sense. We pour water all the time, maybe not into gigantic wine glasses, but we understand the principles on which it works, whereas calculus is very abstract, okay? And it's a bit harder to understand, okay? So, let's think about this situation and think about what kinds of things we know that can help us understand what's going on, okay? So for instance, the very first thing we noticed was that it was a cone, right? It's a cone. So why don't we draw one? Let's draw a cone. There's a cone, okay? Now, we've got some measurements that I told you before, okay? Which measurements will be most important? Well, we've got a diameter, okay? But for our purposes, probably going to be more useful to actually say a radius, isn't it? Okay? So with a diameter of 24, we have a radius of 12 centimeters, or thereabouts, okay? Now, I've provided to you the height of the whole thing to be 24. Okay? There you go. Great. So, I suppose if we wanted, we could work out what the volume of the whole cone is, couldn't we? What is the volume of the whole cone? What's the volume of the cone? It's a third pi r squared h. It's just like the cylinder with the same dimensions, but it's a third the size, okay? So in this case, what are we looking at? You've got a third pi r squared, that's 144, times 24. What's that equal to? Someone got a calculator there? 4608. What's that approximately? I'd like to get a number on that. I'm guessing it must be sort of in the 14, 15. No? Yes? No? Something else?
Sorry.
Can someone give us a more accurate number? A third time. That should, so it's 8. 8 times 144. 1152? Okay, yeah, that does sound like it's better. So we're looking at about what in the 3500s. What do we got? What's the number equal to when you evaluate? 3619. Now, what are all these units? They're all in centimeters, aren't they? I've got 2 of them here and I've got 1 here, so we're getting cubic centimeters. Yes. Does that seem about right? Cubic centimeters. About a 3-liter container. Admittedly, I did make it a little bit bigger, so I think we're in the right ballpark, okay? For this imagined cone that we have, which is kind of similar to this one, okay?